Hello and welcome. D.U.I.S. Differentiation under the integral sign. Okay, this is mainly for undergrads, probably first year in maths degrees or maths degrees or other mathematical degrees, but also somebody who just perhaps is interested in maths and have basic knowledge of partial differentiation, which is not difficult, should be able to follow this. Today is going to be just an introduction, so let's have a look at where do we start with this and what this is all about. Let's write first of all an important result, and this is Leibniz. Leibniz, does it have a T? I don't know. I hope I'm not misspelling there. Leibniz integral. My spelling is really bad. Integral rule, if you want. And what does it say? This is quite something. The proof of that is beyond the scope of what I'm going to do today. I'm just going to write it down just to see what this is all about and where it's coming from. And it's not to be confused, by the way, with Leibniz formula, which I think is to do with repeated differentiation of products, which I think now you actually do it at A level. So Leibniz integral rule says the following. Suppose we have an integral of functions of a function f, which is of two variables, let's say x and t, and we need to integrate it with respect to, let's say, t, and we have variable limits. So the limits are a of x, these are functions of x, and b of x. Okay, and suppose we differentiate this particular expression with respect to x. Because it's a function of two variables, you can actually use the ordinary derivatives. It doesn't really matter. I'm going to differentiate this integral with respect to x. What happens? This is the answer, so don't be scared by this, because we won't be doing anything like that, neither will we prove it. So we're going to get the following. We're going to get f of x b of x times db of x by dx minus, so that's the top limit basically. I'm substituting my top limit for your t times the, by the chain rule, the derivative of b with respect to x, and then I'm subtracting x a of x times the differential of a of x with respect to x, and then we got the final term, which is the one that is of interest to us, plus we're going to have now a of x and b of x, and we're having now d by dx of f of x t, okay, dt. So quite something, a total mess. And as I said, we're not going to be proving anything like that. I think I've seen the proof when I was doing my degree a very long time ago. I'm not a purist, I'm not interested. So for this particular formula, what is of interest of us is the special case where a of x and b of x are not functions of x. I'm going to write them with a different color pen up here. And we're going to ask ourselves the question, suppose our a of x and our b of x, they're just a constant a and a constant b. How does this thing change this? Okay, this will be, of course, integral a to b, no problem. But then we'll be differentiating a constant. This is the constant b. I'm not even going to bother. Okay, let's change it. B there, a there, a there, a and b. Okay, this term here, because when differentiating a constant, produces 0, vanishes, and so is this one here. So all of this will be gone. So this particular formula reduces to something very simple, and we have to see what it actually says. It says d by dx integral a to b of a function of two variables x comma t with respect to t. It's exactly the same. I'm looking at the only surviving term here, which says it's the same as the integral a to b partial d by dx of f x comma t, oops, very bad dt. So what does he actually say? He says if we have constant limits, integration and differentiation commute. If we want to differentiate this with respect to x, we can actually move it inside the integral, so long as the limits are constants, and of course the functions are well behaved. I'm not looking for sort of strange, bizarre things that don't obey. I think purists can make constructions of some bizarre functions. We're looking at the ordinary functions like sines, cosines, algebraic powers, exponentials, and so on. All of these functions are well behaved, and this particular rule is very, very important to us. That's what he actually says up there. I didn't actually write it in full. Differentiation under the integral sign. Today what we're going to look, we're going to look at probably at a couple of examples, time permitting, and they're not going to be practical examples. They're not the kind of examples you might get the wrong idea from what I'm going to put on the board, what this is all about. You're going to say, is that it? What's the whole point of this? These are very powerful techniques that will allow you to integrate some disgusting integrals eventually. But for today, I'm just going to look at a couple of integrals which we can actually do with A-level techniques, just to actually play a little bit with this particular rule. So let me start with the first example, and we're going to look at the integral 0 to 1 x to the power of 4/3. I'm using this because I'll pick this particular question from one of my books. You will find this differentiation under the integral signs, by the way, ladies and gentlemen, and the booklets advanced, and I think the file, the PDF, is actually called differentiation under the integral sign, as I'm calling it up there. So this is one of the questions there. It's right in the beginning, dx. So I use power of 4/3. Of course, is this a difficult integral? Absolutely not. I mean, it's just a single integration by parts. The only thing we got is it's improper because of the limits. So the question is, what is that equal to? And where do we start with something like this if we want to use these techniques? The first thing to notice is if we differentiate, let's say x to some power t, we're going to call it a parameter, but for the time being, think of it as a constant even as you're just looking at it. Okay, x to the t. We can do, of course, two types of differentiations. We can differentiate with respect to x, but we can't differentiate with respect to t. And it's the differentiation with respect to t that we're looking at. So suppose now we treat this parameter as a variable, if you want, and we say, okay, what will happen if I do d by dt of x to the t? Okay, this will give us, of course, this is a constant now, x to the t times the log of x. Okay, that is practically what we got in there, but our t ought to be 4/3. So my starting point for something like this, I'm not going to put the 4/3 in. I'm going to say, okay, let's try to integrate 0 to 1 x to the power of t log of x dx, where of course, if I find what the answer to this integral is, all I need to do is plug t is equal to 4/3 and I'm done. Okay, what's my next step? Well, what I've got in the integrand here is in fact this. We just say in this particular line, and it's good to replace it. Then this partial derivative, we got constant limits, okay, we can pull outside the integral. So d by dt, integral 0 to 1 x to the t with respect to x. That's a very easy integration, isn't it? X is at the bottom, so this, of course, d by dt, put straight line there, it's not quite straight, increase the power by 1 and divide by the new power, subject to t, of course, not being equal to -1, and the limits, of course, 0 to 1, and to be perfectly accurate, we need another set of brackets in there. All right, let's evaluate this. It's not difficult to evaluate, of course. We're going to get d by dt still on the outside. And if we plug in there 1 for the x, okay, we're going to get 1 on the top over t plus 1 as we got in there. And if we put x is equal to 0, that of course is equal to 0. Let's put it minus 0. So nothing else is being produced in there. And of course, that's a very easy differentiation to do, is with respect to t. And this, of course, will differentiate to minus 1 over t plus 1 all squared. So what we've done so far is we found the integral of 0 to 1, x to the t log of x turns out to be this particular expression where t can be any value there except minus 1, really. Okay, so what's the answer to our integral? Well, our integral is exactly that, but for t is equal to 4/3. So all we need to do in that last line is to say, I'm going to rub off a little bit of the workings up there and return to my original integral. I put question mark in there, but now we know the answer. The answer is minus 1 over t plus 1, where t is equal to 4/3. 4/3 plus 1 all squared. 4/3, 7/3, 49 over 9, which I hope I've done it correctly, minus 9 over 49, and not the site, of course, of any limiting processes with because of course this integral was improper. And I'm not saying at all that this is actually easier nor quicker, okay? It's just an example that has theoretical value rather than practical value, but it's important to go through a couple of examples like that before we see the real thing. I personally think the real thing, when you're actually using differentiation under the integral sign, for some of the standard integrals that this technique is very useful for, are in fact easier than some of the examples that I'm going to do today. Today, let's do one more. So the second example, it's again in my booklet up there. See if I remember, before the lecture I did look at a couple and I thought to myself, I'm going to do those two. I think it was 8 over, otherwise if it's not that, I have to abandon the lecture and say, okay, I'll leave it as homework for you. dx, usual things that teachers do when they can't do a question. Okay, I think that's the integral, and I think if my memory serves me well, I think the answer for this was pi plus 2. Can this integral be done without differentiation under the integral sign? Very easily. In fact, this is done by using a substitution. X is equal to tan theta, and it's not difficult at all. It needs a bit of trigonometric application in there, because you're going to get probably with sine squared or cos squared or something along those lines to integrate, but it's not hard. So where do we start with something like this? Let's look at the expression, first of all. The 8, by the way, makes no difference. I think the reason the 8 is there is to make the numbers nice. If that was a 1, it'll be pi over 8 plus a quarter, which will be very ugly. And for us, that's going to be a bit of an additional pain having that 8 in there, but it doesn't really matter. So we're going to look at the integral, the expression, first of all. Let's say 1 over a squared plus x squared. So I have replaced that 1 in there with a squared. Okay, so and I'm going to attempt a differentiation. I'm going to treat this a as a parameter. So I've got two variables essentially in there, and I'm going to differentiate this with respect to a and see what happens. If I differentiate this with respect to a, what will happen in there, I'm going to get, of course, a minus 2a, because that's to the minus 1 times the differential of that. Remember, it's with respect to a. And of course, the denominator is going to go squared. So this is what we're going to get. If we look now at what our target is, which is 8 over 1 plus x squared, it looks like our target for a is equal to 1, but we don't have this particular thing. So probably the easiest way to deal with something like that is to divide both sides of this equation. So we're going to move that 1 over negative 2a in front of the d by dA on the left hand side, d by dA. So all I'm trying to do at this moment is to try to get this to look as close as to the integrand of what I'm trying to find. So it's 1 over a squared plus x squared. And I forgot the squared there, beg your pardon. I did say squared when I was doing it, and I didn't write it. You must know I'm very error prone. I'm just sometimes copying from one line to the other, and I don't know what is happening in my brain sometimes. Okay, so this is now so far, I've divided this term, and in order to make it even better, I'm going to times both sides by 8. So I'm going to do it as it is there, 8 and 8 here. So this is definitely the same as that. And of course, this is exactly what I've got in there, but for a is equal to 1 if you want. So I'm going to look now, instead of looking at my integral as it is up there, I'm going to look at the integral of 0 to 1 of 8 over a squared plus x squared all squared dx. This will give me my answer to what I'm trying to find, so long as at the very end I substitute a is equal to 1. And this is this. So essentially I can put inside the integral, this is the integrand now, in there I can replace it with all of this. I'm going to tidy this mess as well. So I'm going to say that's the same as the integral 0 to 1. That's going to be minus 4 over a, and I wish I could just take it, copy and paste there, but I can't on the board. So that's an a, and that is d by dA. I'm just copying it. Very, very annoying. A squared plus x squared, and of course I have the dx. I hope I've copied everything that I need to copy before I rub anything off. Hopefully no mistakes in there. Okay, where do I go from there? First of all, let's check. This is dx is with respect to x. This is a constant as far as the integration is concerned. Let's pull it outside the integral. So it's going to be minus 4 over a. Maybe I should have just thrown the minus away and swapped the limits. It doesn't really matter. Let's leave it for the time being. 0 to 1. This is now d by dA. The integration with respect to x by differentiation, the integral sign, Leibniz rule if you want. I can pull that outside the integral. I didn't leave space because I'm stupid at times, so I have to write it again and do it on the next line. So d by dA of 1 over a squared plus x squared dx. I have to be careful because my a sometimes, if I write them very badly, they look like x's. So far so good. Now, this d by dA can go outside. I'm going to write it here. So that's going to be minus 4 over a, which was already there, d by dA, pulled outside the integral, 0 to 1. And now what I have to integrate is something which of course is a standard result, a squared plus x squared. That's the whole point, that I've done what I've done in there, dx. Okay, that's a standard arctan. So I'm beginning my integration is with respect to x. It's just a constant. So minus 4 over a d by dA, and this will integrate now to 1 over a, standard result, arc tan of x over a. I should really use 2 sets of brackets. That's for the evaluation. That's 0 to 1, and this is for the operator, the differential operator. So far so good. I just got to do a little bit of a tidy, substitute my values and get my result, hopefully. So I'm going to write it here somewhere. So minus 4 over a, minus 4 over a. Can I differentiate that? Not before I evaluate it. And bear in mind, I'm glad I left the previous line there. This is dx, so that's from x is equal to 0, because you might be wondering, what am I substituting in there? To x is equal to 1, okay? It's not, the a's are just constants for this particular integration. So minus 4 over a d by dA, and putting now x is equal to 1, I'm going to get 1 over a, which of course is not a constant for this differentiation, arctan of 1 over a, arctan of 1 over a, and when I put x is equal to 0, the arctan of 0 is 0, so the whole thing is gone. I'm not going to put minus 0. That is going to give me my answer with the limits given. So how do I want to get my answer? I've got one more step to do there, which is to carry out a differentiation with respect to a, which of course is annoyingly a product rule for this particular one. Minus 4 over a, differentiate the first item with respect to a is minus 1 over a squared. This is really messy, this one. I hope that I haven't done any mistakes. Times the second one untouched, arctan of 1 over a, plus, leave the first bit alone, 1 over a, differentiate the arctan of 1 over a. Okay, that is, let's deal with the chain first of all. The 1 over a will differentiate to minus 1 over a squared, and the arctan, I'm not going to simplify it, it's going to be times 1 over 1 plus 1 over a squared. It looks very messy, but I'm not going to tidy this up, because all I'm going to do, if you look at, this is this integral here. That's the answer. Okay, in terms of a, of course. Okay, my integral, the one I'm trying to find, which I think it was pi plus 2, is exactly the same integral, but for a is equal to 1. Okay, so all I need to do is to replace a is equal to 1 in this particular expression, and a is equal to 1 makes things very, very easy. So that's going to be minus 4. That's going to be a 1, so it's minus the arctan of 1, which is a nice number, plus 1 over 1, which is 1, minus 1 again, so this is now a minus again, and if I put 1 in here, that's going to be 1 plus 1 minus a half. Okay, and I think this should work. Let me just multiply it out. So it's going to be 4 lots of the arctan of 1. Yes, it's all good. Plus 2, and of course the arctan of 1 is pi over 4, and times by 4 will give you pi plus 2, which is what I wrote up there. I did remember the answer well for this particular one. This is quite hard, this particular one, and I promise you the actual practical examples that we're going to look when this is going to be useful to do some disgusting integrals is it's not even as bad as that. I think that was quite involved for such a simple integral, which we can do of course with A-level techniques. But I hope you find it useful, and I am laughing now.